you, and then this guy. Okay. How many finals do you have this week?
Um, Not too many. I think I only have about 4.
Okay, and hopefully they're not all on the same day, right?
Yeah, I've already taken some of them, so I'm almost done.
Yeah, that's good. I bet you're excited.
Yeah.
Okay, so what is this? This is for, so it wasn't a final for physics, but you might have one this week. Is it going to cover everything?
Yes, what the pictures I sent are my final.
Yeah, makes sense. So, okay, you want to just kind of start at the first page? Looks like there's the
Yes, please.
prerequisites. Okay. All right, yeah, so the prerequisites, we got unit conversion. All of these are the same. Well, you got to convert the units, right? And it's really knowing about the prefixes, right? So, for example, one is 27.7 millimeters. And right away you think, okay, meter, right? That's the key. And you say,
Mhm.
what is this equal to? And just go straight to meters. And you say, well, milli is equal to 10 to the negative 3. Did you guys use this notation? We did, right? Scientific notation
Um,
or no?
yes.
Okay, and you're familiar with it, kind of.
Mhm.
So yeah, okay, good. This is then 10 to the negative 3. This is the intermediate step, right? But this is how you kind of think about it. And well, what are our units? Just regular old meters, right? If we wrote it out, it'd be millimeters. But then how many kilometers is this, right? And so how do we get to another pair of kilometers? Or I'm sorry, another conversion to kilometers. And so you can think about it like this. If you have meters, and then you say, okay, 1, and then how many kilometers in a meter, right? So we want to divide by meters. So there are 1,000 meters in 1 kilometer. And so when you go through this and you cancel it out to get meters, and then so when we divide here, we will get 27.7 times 10 to the negative 6th. Now, you may already know that it's, and this is kilometers now, right? But
Mhm.
you may already know that you don't have to show work and there's not any room for work. And so that's why I'm just going to spend that time on this one. But if you just know the conversion already, and if you know that, well, there are 10 to the 6th millimeters in 1 kilometer, or this means the same thing, in 1 millimeter, there are 10 to the negative 6th kilometers. Sorry, my writing's a little bad. I'll try to be better. Then you can just simply say, oh, forget all this stuff. I'm going to go up here and, well, 27.7 millimeters. Well, this is 1 millimeter. Well, so this is obviously 27.7 times 10 to the negative 6th kilometers, if you
Okay.
kind of know that already. But if you're not familiar, not okay with that, because some of these are weird, right? Hectoliters, what's the prefix? Hecto. That's
100.
100. Yeah. Usually they use, let's see, deci. Yeah, it's got to be 100 because there's no other ones. And so, and if you know that hectoliter to centiliters already, or 100 to centa is which, how much is centa?
100.
Yeah, 10 to the negative 2 though. So 1 divided by 100.
Oh, okay.
Like centimeters is 0.01 meter, right?
Mm.
Or 1 cm. I think you're okay with that. Well, that's 0.01 meters, or 10 to the negative 2 meters. And that's why centa, of course. And this, I'm not sure, you may have a sheet for this, but you want to know these, we call them prefixes, like I said, milli, kilo, kilo,
Mhm.
whatever, centa. And so, well, like we said before, so if we want to go from hecto to center, you said 100, I believe that's right, hecto, okay, is 100, or 10 to the 2, right, because 10 squared is 100. And so
Mhm.
what's the difference between these guys? Well, 10 to the 4. Is that part clear enough?
Mhm.
Okay, good. So then it'd be 5.6 times 10 to the 4th centiliters. And so, and that's a good point here too. There's no prefix on the next one. It's just bytes, just like there's just grams in the next one, or just meters, right? But
Mhm.
giga is 10 to the 9th. So it's exactly what you wrote, 512, and then 9 zeros, whatever, right? So hopefully it sounds like you're pretty good on that. So can move past it. How about on number
Um,
5? Go ahead.
I was just gonna say, so this is one that my teacher did, and so I thought it was just going from giga to base, but I don't know any if that's right.
Oh, yeah, yeah, yeah. No, that's right. Yeah. Because for this, everything we've been talking about, giga, well, that's 10 to the 9th, right? And
Hmm.
so let's say you have, that's all we're saying here. And 512, well, GB, gigabytes, right? Well, it's 512 times 10 to the 9th bytes, for the same reasons as we just talked about on number 1 and 2.
Oh, okay.
Yeah, I triple checking myself, but yes, that's definitely right. Just like if you said, let's just for a second say 512 kilometers. Well, what is that? It's 512 times 10 to the 3rd meters, right?
Hmm.
512,000 meters. And so we know, since this is definitely giga, I know that we did it right. That's kind of a check you can have if you're really familiar with your prefixes. Like for the next one, nano, or N is for nano, right? And nano
Hmm.
is 10 to the negative 9th. So this one would not be right for that. Be very clear. I would say, what is it? 10,750. So 10,750, 10,750 nanometers, or times 10 to the 9th meters, because that's just an N. You can replace that with N. And you might want to, so what were you asking me if that is actually correct on the bytes? It depends on if he wants you to have it in scientific notation, right? So
Hmm.
this 512 gigabytes, it's your number right there is definitely, there's nothing wrong with it, but he may want you to say, okay, 512 times 10 to the, excuse me, 12 or ninths, right? 9 bytes. But then this is not technically fully correct. If you have to do scientific notation, you have to say, oh, 5.12. Well, how many times do we move the decimal? Twice. So 10 to the 11th now. Make sense?
Hmm.
Okay, cool. That, and it looks like, and it's the same with that one on the grams. Oh yeah, that makes sense since there's 4. You want to put that, you probably want to put it in, 1.05, and then, well, how many times I have to move to get it there? And it looks like 1, 2, 3, 5 times 10 to the negative 5th meters, grams.
Okay.
Anything else on these conversions? By the way, this is really good for chemistry. I don't know if you've done that yet, or obviously you're going to, but you might, and depending on what you're doing, you might do it in college too. So this scientific notation and this
Mhm.
conversion is super important. It won't go away. So
Could we
yeah,
just do one more example really quick?
yeah, of course. Okay, so how about let's do kind of a weird one, maybe. How about just you might see this later on. Convert this to, what would this be in meters? When you get good at these, you can just say right away. So the process here is to, what is the prefix? I know that, okay, meters, it will usually say, you'll hear it
Mhm.
in words. And then, oh, this is 10 to the ninth. Oops, 10 to the ninth. Okay, well then this must be, well, just 650 times 10 to the ninth meters. But like we said, we might want to put it in very proper. So how many times do we move the decimal place? Well, if we move it to the left, then we have to add to this exponent. So 10 to the negative seventh meters. What about millimeters? What if I wanted to go to millimeters?
Um,
We know this guy's definitely 10 to the third.
mhm.
So it looks like that difference is 6 rather than it being 9 as it was before, right?
Okay.
So then whatever it would be, we can keep that. We want to make it proper. And we would add 3. Yeah.
Okay.
And then, of course, if you would convert that to meters, well, of course, you're going to get that one as a little check for yourself. Sometimes you'll see it going into not the SI unit. I don't know if you've gotten into that, but this is the SI unit, meters, right? It's the standard.
Mhm.
Everything else is not. Good enough?
Mhm.
Okay. How are you on 5 and 6? Do you want to go through them? The convert weird units?
Uh, yeah, I just need like a little brush up on those.
Sure, yeah. So it's all about these conversion factors. And do you want a new one, or do you want me to do what number 5 is and talk you through it?
Um, yeah, let's do number 5.
So right away you're saying parsecs to inches. Like, I don't know. I have no idea. I mean, I really don't know what that conversion thing is, right? Because, and look at it, there's 3 things here. And so the first thing you always write down is whatever it's in. It looks like you're using, usually it's PC, but I think you're using, that's PS, that's fine. It doesn't really matter. Parsecs, fine. And then that's good to a little placeholder for yourself. You can divide anything by 1. And then we're going to inches. And if you knew the conversion factor directly to inches, you could write inch parsec. It's always, my point here is it's always, you're always canceling. Because I can go like that. Oh, and then whatever the number is here to inches. But obviously you
Mhm.
have to go through this entire process that you see in front of you because we don't know that conversion factor. But when you don't know the conversion factor, let's write down something you do know. And it looks like, yeah, well, light year to parsec, that's the natural thing you do in astronomy. So again, parsec on the bottom, because we're canceling it, we got to get rid of it. What do we want to convert to? Light years. Okay, fine. How many light years in 1 parsec? We have to look that up or whatever, but it's right there, 3.26, right? So then you go through that entire process for each one. And again, this is called the conversion factor from, well, from parsecs, because that's what I got rid of, to what's the new unit? Light years.
Mhm.
And so 5.23 parsecs is literally equal to, it's the exact same thing as 17.0498 light years, right? And so I'm just talking a lot about this one. We would use our significant figures. I guess it would be 0 there. And then light year is the unit. But as you did there, and as you see, well, that's not the right answer, obviously. Why? Because we're not in inches. So you can do that, and when you first do it, you do that and say, okay, I'm good to light years now, let's keep doing it. But then as you are, it seems like you're good at, or you're better, you're fine with the conversion now. So you do it just as you said. You say, okay, light year to inch, do I know the conversion factor? Still no. And so what do I know? What is a light year equal to? Well, in meters, right? Yeah, that makes sense.
Mhm.
And so we canceling light years, so it goes on the bottom. What do I want to convert to? Meters. What is the conversion factor? Again, I'm just rounding it differently here than what you have, but hopefully you don't have trouble with that. Again, conversion factor, light years is what we cancel, 2 meters. Okay, I think you get the process, and then you do it again, because again, I don't know what meters on the bottom, get rid of. I don't know that number. You might, I don't know, it might be on your paper, but looks like you went from meters and then to feet, right? And then to inches. There you go. Do you want to see the whole thing worked out, or are you good?
I think I'm good.
How about number 6? Think you can do that one on your own?
Um, we'll see.
Okay. Do you want me to go through it right now, or do you want to save it?
If you could go through it, that'd be great.
Sure. I'm going to do the same exact process. It's always the same. I don't care about anything yet. I'm going to say, this is what I have, divided by 1 as a placeholder. Great. Then you look at, what do I want to go to? Meters per second. I don't know the conversion factor. If I did, I would write it down. 1 mile per hour to cancel, but I don't know this conversion factor. But what do we know? And let's rewrite this to be a little more careful. Let me know if I'm going too fast also. What is MPH? Well, that's not particularly helpful to me. I'd rather see it as 215 miles per hour. This is the same thing. It's equal. That is equal to 215 mph. Why? Because it's 215 miles per hour. You always you divide, right? And now it's a little
Okay.
easier. Now it's a little easier to see. And now I say, oh, miles. Okay. Well, I know this one. This is a conversion factor. What do I want to go to? Let's go to feet. And so that means 1 mile on the bottom. How many feet in a mile? We're converting now from miles to feet, 5280. Great. You could multiply and resolve, and you'd have, well, feet per hour. But we might as well keep going, because we want to do it all in one go, so we don't have to waste our time. So now we need, oh, feet to meters. I know that one. What am I canceling? Well, feet. How many meters? Oh, that's wrong. There are 3.28 feet per meter, right? Yeah.
Mhm.
And so again, I want this on the bottom because I'm getting rid of feet. I don't like it. I want to go to meters. That's my final, whatever idea, my final unit, what we want to say. And now we say, oh, let's, you could do it in the calculator and you say, all right, I don't care what the number is. It's a weird number, whatever. But the units, what are they right now? Well, it's meters per hour. Hey, that's pretty close. Not quite though. But how do we go from hours now to seconds? So do I know the conversion factor? Yes. He may want you to see it worked out. Hours to minutes to seconds. That's not too bad for you, I think, hopefully. And so, but now we got to be careful here. It's not this one. It's not, well, how many seconds are in an hour? 60 times 60, right? Because if you do the minutes, that's right. No, because you have to cancel the hours, and now the hours are on the bottom. So we need to flip this guy around, and we need to say hours per second. That's the unit we want, or the conversion factor is what it is. And now we say,
Mhm.
there we go, hours. Great. Now what's my final units? What I want, meters per second.
Mhm.
And then the final thing, of course, to get your number is put it all in the calculator and don't make a mistake, right? So we got 215 times 5280 divided by 3.28, and then divide that by 3600. So 96.14. And we want to be careful here. We have 4 significant figures. Notice I didn't write that. I don't care, but I do care in the end. So 4 significant figures means it's 0.14 units, of course, meters per second. And when you're doing your homework and stuff, you should go to a little, just even Google. Google's great. And you just put MPH to M/S, and then the Google has a calculator, and it does that for all of them. Nanograms to grams, whatever you want. Parsecs to inches, I think it's got everything. And then you can check your work,
Mhm.
Good on that?
When I put that in the calculator, I did not get that.
Okay, let me make sure. So 215 times 5280, then divide that by 3.28, then divide again by 3600. Yeah. So let's double check. So 215 times 5280 would be 1135 200, and this is meters, fine. And then on the bottom I get 3.28 times 3600, 11808. You may be doing, I can't see what you're pressing, so but you're doing it in a wrong order, I suppose. And you got to be careful
Yeah.
with these.
Um,
Triple check
I
this.
multiplied the. Okay, so I multiplied 215 and 5,280,
Good.
and then I divided it by 3.28 times
Right. So
3,600 when it should have been divided again.
I don't try that exactly. You're right that you didn't do it, because when it does the multiplication, it takes that order of operation and it makes 3,600 on the top. So you're really multiplying 215, 5280, and then 3,600, unless you put parentheses. You'd have to put parentheses around to the left of 3.28 and then to the right of the 0 and 3,600. But what did you get on your division? Because that may not be right either.
When I did it the way that you did, I got 96.1382.
Yeah, and so you did it, as you said, 215 times 5280 divided by 3.28 divided by 360, all in one line, all in one go. Okay, so that's good to know, because sometimes that doesn't work for me. I have to be very careful, because I don't know the calculator. This is what I do. 5280 sounds like it works for you though. I do that, and then I have a result here, and just to be careful, just to be very careful and sure, then I do result and then divide that by 3,600. So two equal signs, right? But if you're confident in your calculator, and you know how it is, and you can do that divide, then yeah, that's fine. And again, Google to check your work when you do these practice problems. And you can find these practice problems anywhere, really. So yeah, prefix, this process of converting weird stuff. Obviously, you can do that process for nanograms, like I showed you on the very first one. That is the process you want to do, but we don't need it for this stuff, because we already know the conversion factor. It's 10 to the -6. Waste of time to do all that, right? But you're going to need it, like we said, for parsecs and inches. And this process, remember this process, it's the way to do it. I guess I did it here, where you just go piecewise. You know what I mean by that? Write down the first thing, that's the process, and then, oh, what do I know? What did I get to? And then write that one down. Okay, and now I say, is that what I want? Well, ultimately, no. But then what's the next one I know? And then eventually you'll find one that is the answer you need, right? Okay. So yeah, we can definitely revisit that. Definitely revisit that as needed. But if you want to, we can move on to the motion, that first problem on the bottom there of the first page.
Yes, please.
Okay, driver slams on the brakes. Let's go slow as the first one there, doing this, just a reminder. Driver slams on the brakes. You read the problem and you ask yourself, I'm going to try to talk you through my thought process here and be slow about it. Okay, I read it, fine. Driver slams on the brakes and changes the velocity of her car from 23.0 meters per second to, and then I stop right there and I say, okay, is there any useful information? And it says changes the velocity of the car. Oh, okay, a change, but they give me one and it says from, that's the key word. And so if I was doing this from the beginning, I'd say from, and I would underline that word and say, that's the initial. That's a keyword, we call this thing. That means VI is equal to whatever it says, 23.0. And notice I didn't finish reading the problem. They say that, I remember hearing that in high school, like read the problem and then go back and read it twice. And I say, no, waste of time. I mean, if you need to understand what's going on, but like, I know this is given information, so there's no reason not to. And it gives me a chance to say, okay, initial velocity, where is that? What is that in? Okay, it must be a motion problem, some sort. It's moving, obviously. So hopefully that's clear. So from, that's a keyword. And then right after that, you'll see that word to, that's a keyword. We call the rest garbage information. A driver slams on the brakes and that's all garbage. I don't care. It could be there, it could be not. It helps and it's a complete sentence, right? But just to, so you know,
Mhm.
garbage versus keywords. This is a keyword two. Two. Okay, that must be a final velocity from two. I think that's pretty, hopefully that's pretty clear for you. You seem pretty smart, so I think you got that. So we have that. And remember, keyword final velocity. Oh, also, I want to ask you, what are you using? F and I. Okay. Sometimes you'll see V1, V2, but it literally doesn't
Mhm.
matter. You're using capital. Let me be consistent here. Capital S is fine, whatever you want to do. Okay, in 4.10 seconds. Great. Again, what are we doing? This is extracting information. Again, that step. I recommend doing this all the time, every time. Okay, 4.10 seconds. What is that? Oh, it's seconds. That's a time. So what do I represent as time? Well, it must be T, because that's what it always is for now. And then I can write S. Cool, this is all given to me. And then it says determine the acceleration of the car. Well, keyword determine, that's telling me what I need. It says determine acceleration. What's the variable for acceleration? A, cool. I'll put a question mark. Could draw a picture here, and a picture could be useful, not particularly in this problem, but it's good practice, and I would encourage you to do it. We're not going to do it right now, but for harder problems, because there's going to be problems harder than this. And it's useful to say, okay, here it is. Here's the initial velocity. Here's the final velocity. Some time frame, delta t, right? Or sorry, just t. And what happens in between this time interval? There's a change of velocity. That's what acceleration is. Okay, so
Mhm.
that's literally what's happening. Okay. So then picture if you need it, fine, and then identify. Identify what? The equation that relates all of these things. And that's exactly what it says on the paper. The equation is, well, A equals a change in velocity, which is some final minus some initial. Think slope from algebra. If I don't want to confuse it too much, but it's just a change divided by a change. And change in independent variable or rise over run, right? That's what acceleration is. It's the slope of the velocity versus time. And now it's easy because we say, oh, I have all this stuff. I can easily solve for that. Now calculate is the last step. And you plug in your numbers. And it looks like you get 20 divided by 4.10. So it'll be like 4.8 something. Let's do it. 4.87. And then units, you want to know this, of course, is meters per second squared. If you forget that, you can always say, what is the units up here? Oh yeah, velocity. I know that one. That's meters per second. That's not too bad. Then I divide by seconds. Well, remember how to do basic fractions. And you say, oh, this is actually this. Oh, S, anything times itself. That's what this square business means. Okay. Any issues or questions on that one?
Um, I'm still trying to put it in my calculator. 1 second. Okay. Okay, I got the same answer.
Yeah, 4.88. And you say, you can, if let's say this is something you would do, and if you have, I would recommend doing this even on a test, and you say, is that reasonable? And it's hard to say because we're not familiar with acceleration. But like when you slam on the brakes to avoid an accident, right? It's a fast acceleration. It's a change in velocity. Like, so if you go from 60 to 0, well, how long does it take you? That's your acceleration. If it takes you an hour to go from 60 to 0, well, you're not going to feel that probably, but if you do it in a second,
Mhm.
you're going to go through the windshield probably, right? Because of Newton's second law.
Yeah.
Large acceleration means a large force. And so if we got something like 480, be like, well, that doesn't make any sense. I mean, that's a rocket ship basically. Just a mental check, to make sure you did everything correctly. Okay, I'm not sure which the second page is here. Let's see if we can find it. It's probably more motion problems.
That one is the race car driver, the airplane, and then it goes to forces in motion.
Oh, right there, above it. Excellent. A race car driver makes a lap around. Also, your picture might finally be useful. But again, I mean, it's a different problem, and hopefully it's clear. I'm literally going to do the exact same thing I just did. Process is always the same. Look at it, determine what is the given information is, and assign your variables, and decide if what's garbage information, what's not. A race car driver, don't care, makes a lap, might care, not sure yet, around a 4,025 meter long track. Okay, that's a distance. Why? Because of m meters. So I think you're using d, which is fine. And we know this is given. Great. And they do it. So they make a lap. Sometimes I do a picture at the same time. It's not, it doesn't seem like it's entirely needed, at least to solve your problems, but it can be helpful. And you say, oh, okay, the circumference of the circle, if you want to get real fancy, is 440.25. And he does it in a certain time frame, t. Right. And so you can say, done long track in 48.7 seconds. Okay. Given information, it must be time because it's seconds. Variable for time is t, 48.7, and then s. Great. That's that sentence. You know, we've fully extracted the information we need from that first sentence. And you keep going, obviously. Determine the average speed and average velocity of the car. So picture is very helpful here. So I'm glad I got that already. Lap, don't tell us it's a circle, but it doesn't matter. In this case, it could be a circle, it might not be, you know, it could be like I think racetracks are actually more like this usually, whatever, like a track field. So now we say average velocity, average speed, usually s. I'm not sure forget what you're using. I don't think we covered this actually. And then velocity. Velocity is a vector. Sometimes you'll see it with an arrow, you may not, but v is definitely reserved for velocity. Okay, what's the equation that relates all these things? You know, and go back to your picture. That's kind of, I'm talking out loud for the thought process, right? Because that's always the next step. Identify what the equation that relates everything. Okay, and you may know already. Well, s, or average speed. Okay, do you know if you're using? It seems like you're following good or well enough, hopefully. But sometimes you'll see v average for speed. Well, I guess that's average velocity. Are you using s for speed? Average for speed? I want to make sure I'm
Wait,
using
S or F?
average speed. Do you know? I want to make sure I'm using the thing so it's as easy to understand as possible. If I'm using a different variable, you know what I mean? I don't want to confuse you. For S, for average speed, is that okay?
Yeah, I think we use S too.
Okay, good. So yeah, average speed, we know the equation for that. Speed is, what is that? Distance divided by time. Because speed, if we think meters per second, well, it has to be, because meters per second, the only way to get that is d divided by t. Great. And you know, you can do this right now, and let's do it. Calculate the average speed. Remember, well, let me do it first. 40.25 divided by 48.7. Okay, whatever, 82.6 units, meters per second. Why? Because we have meters and seconds here. Everything works out. This is one of the answers. Which one? Average speed, S. Now, this is where you have to understand the difference between a scalar, which is just a number with units, and a vector. So I'll say it again. This is a scalar, like time is a scalar. Why? Because it's just a number and there's units. Or the number of apples, 5. The scalar. Okay, so drill that in your head. And it's pretty easy. It's like, well, why do we care? Well, because we care about vectors, and we have to know what a scalar is to know what a vector is. So a vector has all the components of a scalar, which what is a scalar? It's a number in units, usually. Not always units, but it's always just a number. 3 or 10 or a million, I don't care. There's my number. There's some units, but now the vector also has direction. And that's the difference. And I think that makes sense to you. Imagine going to the store and you told somebody how to get to the store, or just down a straight road to your house or whatever. And you say, go about 2 miles. And they say, oh, okay. Which direction? You need a direction. That's why displacement, or kind of distance, well, we call it displacement, but it has a direction. And that's why velocity is actually, it's not distance divided by time. It's displacement divided by time. And to be 100% clear here, we're writing down velocity, which is a vector, which means, oh, what is a vector? It has a direction. So the important point is here, go back to our picture. It's a lap. I don't care where they start. So choose them here. It doesn't matter. And you say, this is where I started. So this is my initial position. Or you can say this. Maybe that's a little more clear. Di, initial distance or initial starting point, right? Is that clear? Are you still there? Oh. Hey.
Hi, I think we got disconnected for a second.
Oh, okay. How long was I yammering with to no one? Did you? So where did I leave off, or where did you?
We were talking about how a vector has direction, and that's how it's different from scalar.
Which just has, scalars only have what?
Units.
Number and units.
Yeah.
Yeah. So like 50 meters. Great. 50 meters is just, I think I started getting that. And you say, did they get the house analogy? I said, or you're going to the grocery store, you got to tell somebody how to get to your house, right? And so yeah, you say, oh, it's 2 miles. And then they say, oh, cool. Which direction? Right. So that's why vectors are important because, okay, good. Now I started getting into it and it was velocity here. We have velocity, which is displacement. Does that sound familiar? Did you guys talk about displacement at all?
Sort of. It sounds familiar.
Okay, good. Because that's what we call it. Sometimes we use X, but I will continue using D because I'm not sure what you're doing. And why I have a big triangle here, but it just means a change, just like rise over run from slope. And so some final minus some initial divided by time. But it's really important to remember vector, direction. Not only does it have the components of a scalar, which is a number and some units, it also has a direction. And so I'm going to skip ahead here. The average velocity is 0. You still want your units, meters per second, fine. And I'll explain why. And it's because that velocity is a vector and it only depends. I don't care what I'm doing in between. For average speed, like it really matters. So check this out. Here's your house. Here's the grocery store. And I mean, you know how, you're a person and you go out. And so you know that it's, well, I don't just go there, right? Obviously not. I got to go down. I got to go out my driveway. And then I got to go here and I got to do all this stuff, right? If you were a bird, as the crow flies, as they say, that's what the difference is. That's the vector part. It's the distance from one point to another. I don't care if I went like this and I said, oh, there, yeah, that's a long distance, right? Somebody like, well, you're an idiot. Why don't you just go on the streets? And this is a long distance. Yeah. Oh yeah. But I don't care. I don't care about that. I only care about this. That's the only thing I care about when I'm talking about a vector. That's it.
Okay.
So that's why this thing is called displacement. This is getting, the big arrow is display, or the big line here is displacement. But then this guy here is total distance traveled. And that's the one we use in speed. That's the difference between speed, average speed, whatever, and average velocity. Total distance traveled. It's still d divided by t, time taken to go around this crazy old path, right? But the velocity only, this is it. That's all that matters. I don't care. Even if I go this way, my velocity is still just this distance here. Call that delta d, or just like it's a change. Just the final and initial points, right? Where this is the final point, df, and this is the initial point, di. Again, divided by time taken, right? But notice that, yeah, this is going to be a very slow velocity because it's going to take a lot of time if you go along this crazy path rather than, but this is still the displacement here, that line. So going back
Okay.
here, is this clear? It's okay if it's not. I will try again. Why the average velocity for this problem, number 2, is 0.
It's 0 because you start and stop in the same place.
That's perfect. I literally couldn't have said it better myself. And this is how we say what you just said in mathematical terms, right? The final position is the same as the initial position. And then if you look at the math, the velocity is 0 because, oh, I'm taking a difference,
Mhm.
right? Just like if I subtract the same things, what's 2 minus 2, right? Well, 0, obviously. And so if this is true, I get 0. Good.
Wait, if you subtract, wait, what from what?
If you subtract, so the equation for velocity, remember, is just depends on the initial and final points. So
Mhm.
df is equal to di. Sorry, the velocity is this equation, the
Okay.
final position minus the initial position. So when you subtract initial from the final, right? That's what I was saying. You will get 0 if they are the same, of course.
Okay.
Is that clear? That's if you understand this problem, then you've got it. You got vectors, you know, the difference between vectors and scalars, as well as this can be confusing, speed and velocity. And this will definitely be on the final, speed versus velocity. So
Okay.
yeah, maybe come up with your own example, you know, thinking about scalar versus vector. But that's why I like to think, you like to use the house example. If you're telling somebody how to get to your house or where to get somewhere, right? How to get to the store. And imagine you tell them it's 2 miles and they say, oh, cool. What is that? That doesn't help me, right? Do I go north? Do I go south? And that's when you say, ah, that's a vector because there's a number, the 50 or the 2 miles, 2, and then miles are the units, right? That's a scalar. But now I say, well, you say that direction, you know, or north or whatever. Now it's a vector. Okay.
Okay.
Okay. I can maybe start this number 3 here. Yeah, let's just get it done. Unless you have a question you want to ask for, you know.
I don't think so.
Okay. So yeah, let's do it. I'll do it quick and we can go over it again. I'm serious. Same process every time. Okay. Extract, given information. An airplane traveling at the speed of sound. Okay. So it's traveling and then it accelerates. So it's travels. I don't care if it's the speed of sound or what, but velocity is related to acceleration. So I need to use V. It's 343 meters per second. It's saying it accelerates at a rate. Okay. It's telling me the acceleration. I really know that because of the units. Continue on to the next line, you'll see meters per second squared. That's definitely acceleration. I don't like to write the zeros. You can add them at the end when you're done calculating stuff. And it does it for a certain time frame. Okay. How long? Time, 12.5 seconds. Now, we're almost done, but I made an error. I got to say initial velocity. And I didn't know that until I read the last part, because then they asked me, what is the final velocity here? And so I know, oh, that must be the initial. And it's telling us that at the beginning. It's traveling at the speed of sound. That's the initial velocity. Okay, great. And then picture, not needed really. And then I identify the equation that relates all of these things. Well, we know what that is, right? It's A is equal to VF minus VI divided by T. And from there, you can solve it. If you want to do it real quick. Oh, right. We got to solve for VF, right? So why don't you walk me through how to solve for VF? Because that's what we want, right?
Yes. So you're first going to multiply by t on both sides to,
Good. So what's the new equation?
and then it's t times a equals df minus vi.
Good. I agree.
And then do you just divide? Wait, hold on.
How do
And
we
then
isolate this guy or get it by itself?
you divide by vi.
So if I'm isolating, I got to get it by itself. That means I have to cancel. How do I cancel minus vi? I have to add vi, right?
Oh, yeah. Okay.
Good. Because of course, anything, I mean, you can rewrite this as vi minus vi, right? Of course. Or minus vi plus vi, of course, is 0. So that means 0. And then you're left with, of course, you can rewrite this as vi plus at, usually how it's written. But notice I've just moved things around and even switched the sides, but it doesn't matter, right? Hopefully that wasn't confusing going from here to here.
Oh, no.
Okay, good. Okay, yeah, that's good. We can definitely go over it again if you want. But looks like we got forces coming up. Do you know when it is, the final this week for physics?
I believe it's Wednesday or Thursday.
Okay, so you got a little bit of time, and you just took that test, and it sounds like you did well. So that's probably a third
Yeah.
of the test, I guess. I don't know.
Hmm.
All right. Well, thanks again. I'll talk to you.
Thank you.
No problem.